Hello and welcome back. This is Chapter 4, Video 6, in which we'll be discussing derivation strategies, including goal analysis and how to deal with subderivations. Two basic issues that students encounter when learning to do derivations are where to start and when and why to do subderivations. We'll talk about both of those in this video. Consider this relatively simple derivation. Where do you begin? Well, we'll look at two different ways for approaching derivations. One starts at the top with the primary assumptions and just gets going in an attempt to reach the goal statement. The second, called goal analysis, or working from the bottom up, starts with the goal and attempts to analyze what steps you need to make in order to reach the goal. For simple derivations, starting from the top and working down often works. But in any case, starting with the goal and analyzing it carefully, that is, working from the bottom up, will always work, and in more complicated derivations is the best approach to take. Let's contrast these two approaches here. Looking at lines 1 and 2 in the primary assumptions, I see that there are some things I can do, so I'll start doing them. For example, line 1 is a conjunction, so with conjunction elimination, I can take it apart into its two pieces. I'll take the D from the left-hand side, and then also one and elimination. I'll take the J from the right-hand side. Now what else can I do? Well, I notice that line 4 matches the antecedent of line 2, so with 2 and 4, I can do a conditional elimination and get the consequent B. Now, my goal was to get D and B, and I have them each in line 3 and line 5, so I can put them together into a conjunction on line 6. And I've reached my goal. So there I worked from the top down, basically just seeing what I could do, and then at some point realizing that I was pretty close to the goal and constructing it. A different approach is to work from the bottom up, to focus on the goal and see what I need to do to get it. Let's see how that looks. Okay, so here is the same derivation over again. So the first step in the goal analysis approach is to take the goal statement and put it in at the bottom of the subderivation. The second step is to ask yourself, what is the main connective of my goal? And here, clearly, it is a conjunction. That strongly suggests, though it doesn't guarantee, that you're going to derive that last line of the derivation by a conjunction introduction. We don't know yet what two lines, but we do know what those lines are going to have to look like. If I'm going to get D and B by conjunction introduction, I'm going to need one line that contains a D and one line that contains a B. With those two lines, I'll be able to make the conjunction introduction. So now we have two new sub-goals. We've analyzed the main goal, and we see two intermediate steps we need to make to get there. So we can focus on those and see how we might get them. For example, if you look at the D, it appears right here in a conjunction, and we know that we can get that D pretty easily by conjunction elimination. So we don't know what exact line number D will be yet, but we do know that it's going to come from 1 by conjunction elimination, so we can write that justification in. We can fill in the line number over here later on once we've completed the subderivation. Now, where is B going to come from? Well, if I look above, I see B is in the consequent of a conditional. And in order to use that conditional to get its consequent B, I obviously need its antecedent all by itself. If I can get J by itself, then I can use it with line 2 in order to get B. I don't have J by itself yet, but I can write it in as a new sub-goal. So I want to get the J. I'm not sure where that J is going to come from yet, but once I get it, I do know I can use it with line 2 to get B by conditional elimination. So the last remaining question here is, where does that j come from? Well, similar to the d earlier, it's right here in a conjunction. So I can very easily use conjunction elimination on line 1 to get it. So actually, that j can be line 3, coming from 1 by conjunction elimination, which means that the next line, b, is line 4, and it comes from 2 and 3 arrow elimination. The d is line 5, and it comes from 1 by conjunction elimination. And our last line here, d and b, comes from 4 and 5 conjunction introduction. Don't worry about all this unused space here. It's perfectly okay. So we had two approaches to this simple derivation, and the contrast isn't as stark as it will be with some more complicated derivations. But in each case, we were able to achieve our goal. The goal analysis method on the right is a little bit more systematic of an approach and will greatly aid you in more complicated derivations. And in cases where you are doing derivations with no primary assumptions or proving theorems, which is essentially the same thing, you're really going to have to apply the goal analysis method because there won't be any primary assumptions to look at. There won't be any top part to work down from. Let's see an example like that. Now here is a rather daunting looking derivation. There are no primary assumptions, and the goal is a rather complex formula. If we read it, it says this: if b then if d then f, then if d and b then f. Where do you begin? Well, you can't work top down here because there are no primary assumptions, so we have to use the goal analysis method. And actually, though this is complex looking, the goal analysis method will basically do all the work for us. So let's write in the whole formula at the bottom of the scope line. So there you have it. Now, the next step, in fact the most important step, is to ask yourself, what is the main connective of my goal? Well, it's going to be a conditional, and in fact, it's this conditional here. So, it's not a guarantee, but that strongly suggests we're going to derive that long formula by a conditional introduction. And in order to do a conditional introduction, what do I need? I need a subderivation. And that subderivation should start with the antecedent as the assumption, and the whole consequent as the last line of the subderivation. So I'll write the antecedent in at the start of the subderivation. B arrow D arrow F, label it as an auxiliary assumption, and now I'm going to write my new sub-goal, the consequent of the ultimate goal, at the end of that subderivation. Now that I have if D and B then F, I can ask myself the same question about that formula. What is its main connective? And clearly, it's that conditional. So that strongly suggests again that that line is also going to come from arrow introduction, which means I need to create a new subderivation in line 2. I will again take the antecedent and put it in as the auxiliary assumption, and take the consequent and put it in as the sub-goal of that subderivation. So it'll look like that. Now F, in that third to last line, doesn't have a main connective, so I can look above and see where it might come from. And in fact, I see that it's here. It in fact is the consequent of a conditional, which is itself the consequent of line 1. So that strongly suggests that F is going to come from D arrow F by some sort of arrow elimination. But in order for that to work, I'd need to have the antecedent D by itself. That is, if I can get D by itself, it can be used with D arrow F and arrow elimination to get me my F. So that's the strategy we're pursuing. Now I can see very quickly that the D will just come from line 2 by conjunction elimination. So I might as well just write that in over here. So we don't know exactly what line number that will be yet, but we do know it'll come from 2 by conjunction elimination. The other question is, how do I get D arrow F? Well, we noted that it is the consequent of line 1. So if only I could have a B by itself, line 1, and that B would give me D arrow F also by arrow elimination. So there are a lot of things in play right now, but the basic idea is we need to get that B, and we can by 2 conjunction elimination. And now I think we can just call that line 3, comes from 2 by conjunction elimination. We can call D line 4, which also comes from 2 by conjunction elimination. D arrow F will be line 5, and I get that from 1 and 3 arrow elimination. And then F is going to come from 4 and 5 arrow elimination. Now, the subderivation running from the assumption in line 2 to F in line 6 gives me D and B arrow F. So I can write that in as line 7, justified 2 through 6 by arrow introduction. Now the subderivation that runs from line 1 by itself all the way down to line 7 justifies our final line, line 8, which is if B then if D then F, then if D and B then F, which seems so complicated to start with, right? And it is just 1 through 7 arrow introduction. So that's an example of how goal analysis can take what appears to be a very daunting derivation and make it a little less daunting. Here's another derivation to demonstrate the usefulness of the goal analysis method. We're given I if and only if L and M as the primary assumption, and the goal is if M and not I, then not L. So again, the first thing we're going to do here is write in the goal statement at the bottom of our main scope. So there you have it. Be sure to leave yourself plenty of space to work with in here. Now, the next and most important step is to ask, what is the main connective of my goal? It is obviously that conditional, so again, I think this is going to come from conditional introduction, which means I need a subderivation taking the antecedent M and not I as the auxiliary assumption and driving towards not L as the goal. Now we focus on not L as the new subgoal, and its main connective is obviously the negation. And there's no guarantee, but it makes one suspect that we're going to get that by hook introduction, which requires itself a subderivation where we assume our goal without the hook, that is, we assume L as an auxiliary assumption, and we're going to try to get some contradiction, Q, not Q. We don't know exactly what those are going to be yet, but if we look above, likely suspect would be the not I and the I. If we can make that work, we'll have the contradiction necessary to do the hook introduction. Now I can easily see how to get that not I out of line 2 by conjunction elimination. So why don't we try that as the not Q? Not I is going to come from 2 conjunction elimination. What that now means is that we want to try to get to I from lines 1 through 3. Seeing how I is the left-hand side of a biconditional, if I can get this piece here, the L and M, then I can use biconditional elimination to get my I. So that is to say my new sub-goal is to get L and M. And the L is sitting right there in 3, so it's going to come from 3, and I don't know what yet, probably 4, by conjunction introduction. But that means I need the M. Right? And luckily I see that the M is right there in line 2. So I'm just going to take it to conjunction elimination. That means that L and M can be line 5, coming from 3 and 4 conjunction introduction. That means that the I can be line 6 from 5 and 1 double arrow elimination, and the not I comes from 2 by conjunction elimination. So what we have now is an innermost subderivation that starts in line 3 with L and winds up in line 6 and 7 with a contradiction. That contradiction allows us to apply hook introduction to get what is now line 8, not L, and we cite 3 through 7 hook introduction. The outermost subderivation, which starts in line 2 with M and not I, leads to not L in line 8, so we can cite 2 through 8 to justify line 9 by an arrow introduction. We've been looking a little bit at the goal analysis strategy, the working backwards approach, and seeing how helpful it is. Another source of confusion is subderivations themselves. When should you start them? How do you get out of them? Let's take a look at some examples of mistakes that can be made, and we'll talk about how to avoid them. So right here is a very simple derivation. The goal just is to derive the formula C. And you might quickly recognize that C is in the consequent of line 2, and so you need to get a B in order to do arrow elimination to get at that C. Maybe you're just not quite seeing that it's right here, and you might be tempted to do the following. Assume a B, because after all you need it. There's nothing technically wrong with that, but it's the wrong strategy for this derivation. Let's see why. Suppose you do go ahead and assume that B. Then in line 4, you can get the C from 2, 3, arrow elimination. Again, there's nothing wrong with line 4 or the justification of it. It's just we're not on the right track here. Let's see why. You might think, well, I'm done with the derivation. After all, I've got C on line 4, and C was the goal, so yay. Unfortunately, no, that is not correct. Why is it not correct? First of all, the point of the goal statement is that it has to be on the main scope line to show that it comes from just those primary assumptions. All we've done so far is show that C, being on the scope line of this subderivation, comes from B plus those other primary assumptions. So we haven't actually completed the derivation. So I need the formula C on the main scope line. You might think, hey, that's easy. I've got C in line 4, so why don't I just reiterate it on line 5 outside the scope line? Of course, reiteration is a rule that allows you to repeat a line. Well, there's a major problem here. You can't exit a subderivation without applying one of the various subderivation rules. You can't move anything out of a subderivation if it doesn't fit the pattern of arrow introduction, hook introduction or elimination, double arrow introduction, double arrow elimination, or V or elimination. If you're not applying one of those rules in the last step, then it's an illegal step and a mistake. Another way to put this is that you cannot exit a subderivation unless you're applying one of the subderivation rules. So actually what's happening here is we're being forced into mistakes because we never really needed a subderivation in this case. We've got the B we want right there, so we don't take line 3 . So we don't take line 3 as an auxiliary assumption, rather it's just 1 and elimination. And then we can use 2 and 3 completely legitimately without any subderivation to get the C that we're looking for, and this is done. So what are the lessons here? First of all, don't start a subderivation unless you absolutely need to, because you can't get out of that subderivation without applying one of the subderivation rules. How do you know when you need to start a subderivation? Well, those subderivation rules always lead to certain kinds of results. An arrow statement, a hook statement, removing a hook, a biconditional, or when you need to deal with a V with V elimination. So make sure you know why you're starting a subderivation and how you're going to get out of it. You should be starting it because there's no other way to get what you need, and that rule will get you what you need. So avoid making assumptions unless you know how you're going to exit the subderivation, which rule you're going to apply to get out of it.